going to talk about reaction mechanisms in this video. When we started talking about kinetics, I said the main questions were sort of how fast is the reaction, and then what can we learn about how it happens. So far, we've looked at rate laws. We do experiments that gives us a rate law, and that rate law lets us determine how fast a reaction is under appropriate conditions, right? At a particular temperature with a particular set of concentrations, what have you. Now we're going to look at the idea of the mechanism. That is, how does the reaction actually happen? What kinds of collisions between molecules have to take place? How does that determine how fast the reaction is? These two things are going to be related because we'll see today that the rate law and the rate itself actually do depend on the mechanism for the reaction. I should say at the beginning, we have had some success at figuring out mechanisms for some relatively simple reactions. There are a lot of important reactions that are very complicated, and it's just not currently and not any time in the immediate future possible to get a really good sense of what the complete mechanism is. But it does still give us some insight about how chemical reactions take place. So here goes. A couple of definitions for us. When I say reaction mechanism, this is essentially the list of individual molecular events or processes that have to take place to get the reaction carried out, okay? We have been diligently avoiding thinking about that, right? We say, well, we know the reactants, we know the products. Now we're gonna think about what do the reactants have to do in order to get to be able to turn into the products, okay? And that can be complicated. We say the mechanism is a series of elementary steps. And so if the balanced equation for the reaction, the reactants are something sort of like the parts list for making the products. The products are the end goal, the finished product. The elementary steps, the mechanism, that's the list of steps that you have to take in order to turn those reactants into the products, okay? When we say an elementary step, that's a very special category of chemical reaction, okay? An elementary step is a chemical reaction or an equation for a reaction that describes an event that would take place at the molecular level. Meaning, if I see an elementary step and it says molecule A plus molecule B react and make products, it means that they do that by having A and B crash into one another. Okay, that says that's just a collision between those two molecules that leads directly to that product. There's a lot of different phrases people use to describe these. They say they're single collision events. Sometimes people say kinetically simple, but elementary step is the word we will use for that, okay? We want to be really careful about not thinking of things as elementary steps unless we're supposed to be, okay? More on that in a moment. If I look at the way we write equations for normal reactions, any old reaction versus elementary steps, they're not really different. And that's confusing, especially when you're just starting to look at such things for the first time, okay? So the top equation there is what is the combustion of octane, which is a reaction that at various times in the textbook we use as a model for burning gasoline, okay? It says, if I think about that in terms of molecules, 2 molecules of octane and 25 molecules of oxygen react to make some CO2s and waters, okay? If you just think about it, the odds that 2 molecules of octane and 25 molecules of oxygen could all just arrive in a single like mass pile-up collision and manage to turn into CO2 and water, that seems really unlikely. Okay, molecules are small. We know they move fast. The idea that we can get 27 of them to all hit one another at the same instant, that's just not a thing that's feasible to think about. So that's very much not something we would suspect would be a single collision event, right? It's much more likely that something starts happening on one end of that molecule, the octane molecule maybe, and we break a bond and then we get something that's more reactive. And so we probably have a large number of steps along the way. The reaction on the bottom is one NO2. We've looked at NO2 a few times. We talked about Lewis structures, right? NO2, remember, has that weird Lewis structure because it's got an odd number of electrons. And so it's got the unpaired electron on the central nitrogen atom. So if 2 of those NO2 molecules bump into one another, you can kind of imagine that those odd electrons, the single electrons on both nitrogens, might really be interested in forming a bond, right? So having those two just bump into each other could well be enough to get them to react. And so that equation is believed to be an elementary step. Okay, so you can't really tell that. There's not like a special kind of arrow that we write or anything like that, unfortunately. So Again, I'm kind of emphasizing a point here that you can't tell by looking at an equation, right? That one that I had before where the 2 NO2s stick together, that one is believed to be a single collision reaction or an elementary step. The one below that still has 2 NO2s reacting, right? Certainly 2 NO2s could bump into one another. They could have a collision, but that reaction is known to proceed by a sequence of steps. It is not an elementary step, okay? Again, you can't tell that by looking at those equations. I can't tell that by looking at those equations. I know that because I happen to have put it in the slides and was looking for an example of something that had the same set of reactants that I could use and say that about, okay? For our purposes in this course, for your purposes, you should only assume something is an elementary step if it basically is telling you that in a problem, okay? If it says a mechanism for a reaction is proposed to be the following and has a list of reactions, that means those are elementary steps. We'll see in a moment, very often, if you're looking at a mechanism and saying things are elementary steps, it will often say like fast or slow near them. That's another tip off that like, okay, that's when I can say this. This is important because there's special things that we can do for elementary steps that we can't do for reactions in general, okay? We're gonna look at that next. One way you can tell something is not an elementary step is by the number of molecules that are involved on the reactant side, okay? It turns out that all the known elementary steps, every reaction that is believed to happen in a single collision is one of 3 categories, okay? There are unimolecular reactions in which there's basically just one reactant molecule. A molecule, maybe by it's collided with something, it has somehow become a very energetic molecule, okay? And it basically just breaks off a piece of itself, turns into 2 molecules. So a single molecule falls apart. That's unimolecular for one molecule. There are a lot of bimolecular reactions. That one with the 2 NO2s sticking together is an example. I have 2 reactant molecules, they collide with one another and they form products. Maybe they stick together, maybe they trade an atom or a group of atoms, but somehow I get different things after the collision than I had before. There are a small number of things that are believed to be termolecular reactions, which is 3 reactant molecules. I've always thought every time I go through this stuff that it would sound better to me if those were called trimolecular reactions, but no one calls them that. So termolecular it is, and that means 3, okay? Both the bimolecular and the termolecular examples, I wrote them here as being A plus B. I could have written A plus A, like in the case of those 2 NO2s reacting. The important thing is that it's 2 molecules that have to collide. Similarly, for the 3 molecule example, I wrote A plus B plus C. That could have been 2A plus B or whatever. It just needs to be 3 molecules that are reacting. There are no known examples of something that has more than 3 reactant molecules that is believed to be an elementary step. And to be honest, like people don't really expect that that's something that will eventually change our view about. There's actually a school of thought that says that it may well be that the ones we think are 3 molecule collisions may just be some pair of steps that happen in really quick succession and that we haven't yet been able to unravel them. But that's kind of an open question, okay? So one way to tell something is definitely not an elementary step is if it's got more than 3 reactant molecules. So that equation I had on the screen before for the combustion of octane that had, 25 oxygen molecules on the reactant side, there's basically no way that's a single collision, an elementary step, okay? So if you're looking at a reaction and it has more than 3 reactant molecules, then you know certainly it's not an elementary step without any further consideration. Again, you don't want to assume it's an elementary step unless you're pretty specifically told to do that. So the reason why I'm trying hard and belaboring the distinction that you can't just arbitrarily go calling things elementary steps is because for an elementary step, we actually can write the rate law for an elementary step by looking at the equation, okay? The justification for this is maybe a little bit complicated, but in the case of the unimolecular reaction, for example, the energies of a collection of molecules are distributed in a way that's similar to the Boltzmann distribution we looked at for the speeds of gas molecules, okay? Meaning in any sample of molecules, there's some fraction of them that have energies above a particular value. That fraction would increase if we raise the temperature, right? But that means if I put more molecules in the container, if I raise the concentration, then I'll have more molecules that might have enough energy to fall apart. And so the rate of my reaction should go up, okay? In a bimolecular reaction, it turns out those will be second order because the number of collisions between A and B molecules would double if I doubled the number of A's. It would also double if I doubled the number of B's, right? Because essentially if I double the number of A's, then the B's have more targets to hit. Same if I flip that around and say I put in more B's, then there's more things for the A's to bump into. okay? Again, if it's two A's, then it just becomes A squared, which is the both being A, equivalent of being first order and first order. Termomolecular reaction will be a third order reaction with 3 concentrations in there, okay? You can only do this if we've said, basically, assuming this reaction is an elementary step, then this is its rate law, okay? I said right at the beginning of talking about rate laws that you had to find the orders of reaction by experiment, okay? And that's still true for reactions in general, all right? But if we're saying we assume this is a mechanism for the reaction and these are the elementary steps, then we can say, if that assumption is right, these would be the rates of the steps, okay? And that's important to what we're gonna take up and how we can relate that to the rate of the overall reaction. So a mechanism is a list of elementary steps. Okay, the previous slide says if I say something is an elementary step, I can write its rate law just by looking at the equation for it. I can say it's first order, second order, what have you. Okay, so if I wanted to propose a mechanism for a reaction, and I should interject and say, I don't ever expect you to get to the point where you would propose a mechanism. Okay, not within the week or so that we're going to talk about things like this in our course. All right, you should be able to look at a mechanism and decide if it is a plausible option in a couple of different ways. And that's what we'll look through now. So if I wanted to propose the mechanism, though, what I would do is I would start by saying I know the overall reaction. I know the reactants and the products for the thing that I'm trying to unravel. Okay. I then basically just make up a guess of what could be a mechanism. And people that do this are people that have a lot more experience thinking about chemical reactions than you do, and would say, well, this is a weak bond, so it might be likely that that bond breaks to get the reaction started, things like that, okay? If I guess a mechanism, I then would set about figuring out what would the rate law be if that mechanism is right, okay? If you think about it, if I know the rates of each step, I can write a rate law for each step. Once I say it's an elementary step, I can say it, I can get its rate law from the equation for it, right? If I know the rate of every step in a sequence, then I should be able to figure out the rate for the overall sequence. That just feels like it's intuitively correct, and it is correct, although sometimes it's complicated, right? If I get the rate law that my mechanism predicts, I would then say, well, I can compare that to an experimental rate law. If it doesn't match, then my mechanism is definitely wrong, right? Because the molecules know the real mechanism. When the molecules react and I measure the experimental rate law, that's the one thing that I can't just say, oh, that was wrong, the experiment, right? I have to trust the experiment. I have to say, well, it's this mechanism that I, after all, just made up and scribbled down on a piece of paper. I have to try and get a different one. I can then do that again, try a different mechanism. If my mechanism does match the rate law, then it's possible my mechanism is correct. Doesn't guarantee it, but it is possible then, okay? So in order to be able to do this, I have to be able to get from knowing the rates for the individual steps to knowing the rate for the overall mechanism, okay? In a very generalized way, that would be a very complicated problem. If my mechanism had 3 or 4 steps, basically each one of those rate laws is its own little differential equation. So then I would have a system that was multiple coupled differential equations. And probably there's a few of you who are ahead enough in math that you're taking differential equations, but that's a problem that's fairly hard as a general sort of idea, okay? Fortunately, there's a very, very simplifying thing that happens in most chemical reactions, okay? And that is the idea of the rate determining step. Okay, rate determining, rate limiting, those phrases are used kind of interchangeably, okay? In lots of chemical reaction mechanisms, it turns out there's one step in the mechanism that's a lot slower than the others, okay? That step usually is one that sort of gets things started. If I have a pretty stable molecule, I have to break a bond someplace so that I have something that's more reactive, okay? That step that's going to do that is often the slowest step. So very often these slow steps happen at the beginning of a reaction. Not always, but often, okay? If I have one step that's much slower than the rest, then it turns out that the rate of the overall reaction is controlled entirely by the rate of the slow step. And those two things actually get to be equal. Okay, that often feels bad, just doesn't feel right to people. But there's a lot of ways, just sort of analogies of things you can talk about for this. One is an assembly line, right? If you were designing an assembly line and you were really bad at designing an assembly line, suppose I'm a worker on your assembly line and I have a task that every time the thing being produced rolls in front of me, I have to do some stuff to it and it takes me 10 minutes to do that, okay? If the person standing next to me has a simpler task and it only takes him 1 minute to do that, then for 9 out of every 10 minutes, that person has to stand there and not do anything, right? Because you can't move the conveyor belt, you can't advance the assembly line until my step is done. So if you watched from the outside just how often a finished product came out of that assembly line process, there'd be one every 10 minutes. Okay. Again, if you were good at designing assembly lines, you'd get those times evened out so that you weren't having so much dead time for things, right? So if you want to make the process faster, you have to speed up the slow step. In the assembly line idea, if some new technology, some new tool made the person with the 1 minute step, made them be able to do it even faster, that wouldn't change the rate of production of the actual product, right? You'd have to be working on the part that is the slow step or the bottleneck, if you want, in the system. Okay, that's the rate determining step idea. And we can do that for a really lot of reactions. And so that's what lets us have a fighting chance of getting from a mechanism to a rate law. Let's look at an example of two proposed mechanisms for a reaction, right? This reaction is one I had up there before. Earlier I said it was not believed to be a single elementary step, right? So now I have two proposed or possible mechanisms for it. If I was checking these mechanisms out, the first thing I would do is see, do they add up to the right stoichiometry? So in both cases, if you add the two steps together, you should find that they add up to the reaction on the top of the slide. In the top mechanism, first one, I have an oxygen atom that is produced in the first step and then used up in the second. That's what we call an intermediate, right? Something that's not a reactant or a product, but it's in the mixture somewhere along the way. In the bottom reaction, I also have an intermediate, but I have a different one. I have NO3 as an intermediate in the bottom mechanism. Okay, so let's look at what the rate laws would be for either of these two mechanisms. Okay, if I come to the top one here, my rate, there's always a rate constant, right? So I get a K. Sorry, that's an ugly K. That's getting worse. Let's try again. That's a better K. When we do rate constants, I'll just make a comment here. In the textbook, we always write them as that scripted font, lowercase k. That's because coming very soon, when we get to chapter 12, we'll be working with something called equilibrium constants, which are uppercase k's, which we always write in a normal Roman font to try and distinguish them. But be on the lookout for that. Don't get your k's crossed up. My rate determining step is the slow one. Right, so the rate is the rate of the slow step, and here that slow step is first order in NO2, so this says it should just be that for a rate law, okay? Bottom mechanism, the rate determining step, the slow step is again the first step. That says the rate now should be a rate constant times the reactants there. I've still got NO2, but now it's a bimolecular reaction. So the lower mechanism predicts that the reaction would be second order. Right? So if I do an experiment and measure the rate of this reaction, I can find out, is it first order or is it second order? Maybe it's neither, right? But if it is either first order or second order, then one of my two mechanisms is still possible. The other one is disqualified because it doesn't get the right answer, right? It doesn't match the experimental facts. So it turns out for that reaction, the experimental rate law is that it's second order in NO2. All right, that says that that mechanism below there could be correct. It doesn't say it is correct because after all, we just made that up, right? If we were doing experiments and interested in this reaction and wanted to dig deeper and find out whether that really was a viable mechanism, probably one of the first things we would do is say, can we design an experiment that will prove that as the reaction is going on, that there are some NO3s present. Okay, they're not in the reactants, they're not in the product, so there's never going to be a lot of them. Anything like that, when it says it's the intermediate, look at the NO3 there. It's formed in the slow step, and then it reacts in the fast step. That means it's not going to hang around very long, right? There's never going to be a lot of them. But if I could get something that measured those and said, yes, there's definitely NO3s in there, that would definitely increase my belief that that mechanism had a good chance of being like what was happening. Okay, if I couldn't find them, then that would maybe make me say, well, maybe there's some other intermediate I haven't thought of and I don't have the right idea down. The main reason why people study mechanisms like this, I guess I should add, is because there's sort of a deep belief that if we can understand the details of how a reaction is happening, that might make it easier for us to begin to get more control over it, to decide, okay, if this is the mechanism, what could I do that would speed it up? Is there something in particular that I could change in the conditions, or by just tinkering with the mixture a little bit and make the reaction go faster? Okay, a lot of people spend a lot of time and effort and money on learning how to try and make reactions go faster, because there's a lot of reactions that are used industrially where the faster your reaction is, the more product you can make every day and potentially sell. Right? So if I'm working on determining a mechanism, these are the things that we would say as a summary of this, right? The mechanism is plausible, is a reasonable candidate if, number one, it has to give you the right overall stoichiometry for the reaction. If I write up a set of steps, but they don't add up to the right reaction, then they're definitely wrong, right? They can't possibly be the right thing. I want it to predict the correct rate law. And then the bottom one, which will strike some fear in some of you, is I want it to be chemically reasonable, is the phrase I chose for that. All right. What does that mean? It means that if I say I have a fast step that involves maybe breaking a nitrogen-nitrogen triple bond, that's going to like really set off my concerns right away, because I'm going to say that bond is really strong. That's one of the strongest chemical bonds there is. It doesn't seem like it should be easy to break that apart, right? So saying that's a fast step doesn't feel right. If I have a reaction in which, I don't know, one of those mechanisms there had oxygen atoms, I think, as an intermediate. If I have a reaction that has oxygen atoms as a reactant, and I'm saying that reaction is slow, then that reaction is probably never going to get to happen, right? Because if there's a lot of oxygen atoms around, they're going to start sticking to one another and becoming O2s. So I can't really expect something that would be as reactive as an oxygen atom would to be a reactant in a slow step. That just wouldn't feel right. Okay, so there's a few things like that you can say, like, no, that one just looks kind of dubious because it's got something in there that doesn't seem like it makes sense. There's a general rule among people that study kinetics and mechanisms in particular that says you can never really say, I have proven this is the mechanism. That said, there are some reactions for which we're pretty confident we know what the mechanism is, but it's always a possibility that somebody could somehow prove there's some other intermediate in there that your mechanism doesn't account for, and then you'd have to go back and tinker with it and say, I didn't have it right after all. Okay. A lot of the ways that people get evidence for this involve, like I mentioned, number one is just detecting intermediates. If you can find the presence of that intermediate species, that gets you a lot of belief that what you're doing is correct. There's also some really clever experiments people do where you can use isotopes to just label a particular reactant, right? So if you have two things that are going to react with one another and they both have, maybe they both have oxygen atoms in them, right? If you start off where one of the reactants has radioactive oxygen atoms in it, you just pick a radioactive isotope, switch to that, oxygen 15, I guess, or 17, yeah, whatever. That's not, wait, never mind, that's the wrong number, but you switch to a different isotope, and then you could actually track where those oxygen atoms ended up. So you could find out, did this bond break or did it not break? And that would, again, help you be able to get more and deeper evidence about whether your mechanism made sense as a possible candidate.